For our next question, we're given the three equations and three unknowns as shown, and we want to know whether we have a consistent or inconsistent system. So our first step, as always, is to ask ourselves if any of the normals are parallel. So we look at our three normal vectors, and we see that normal 2 and normal 3 are collinear. In other words, they're parallel. So we're going to try to determine whether those planes are coincident. Well, looking at plane 2 and plane 3, we can tell that they are in fact coincident. If we want a mathematical explanation for that, it's as follows. Multiplying plane 2 by 3 on both sides gets 6x minus 3y plus 15z equals 33. Plane 3 was given as that, so therefore we have coincident planes. Okay, because we have coincident planes and a third non-parallel plane, we basically have those two coincident planes acting as one, and that non-parallel plane intersecting it along a line of intersection. So what we're going to do is try to establish the line of intersection, and what we're going to do is set up a matrix with only one of the coincident planes in it, because since they're sort of duplicating each other, we really only need one of them in our matrix. And we're also going to use the third non-parallel plane and determine the line of intersection. So we set it up this way. X plus y minus z equals 4, and 2x minus y plus 5z equals 11. And we ignore that third plane of 6x minus 3y plus 15z equals 33 for now. So we set up our matrix as follows. We multiply row 1 by 2, and now we're in a position to subtract and eliminate that entry by my finger there. And while we do that, we can reduce row 1 back to the more simple numbers given here. And that is the matrix that we end up with in that second step. And now what we can do is we can say let y equal t. And by letting y equal t, we're in a position to now solve for z in terms of t. 3t minus 7z equals negative 3, which means ultimately that 7z is 3 plus 3t, and z is 3/7 plus 3/7 t. Okay, now that we know what y is in a parametric form and z is in a parametric form, we can solve for x in a parametric form by going back up to the original, to the top line of our matrix, which said x plus y minus z equals 4. We plug in the parametric equation for y and the parametric equation for z. We distribute and isolate the x. And when we collect like terms, we end up with x equaling 31/7 minus 4/7 t. Well, if we take the three circled parametric equations, in summary, we get this as our three parametric equations of our line of intersection. We can tell that our position vector is 31/7, 0, 3/7, and our direction vector is negative 4/7, 1, 3/7. Since our direction vector is negative 4/7, 1, 3/7, we can multiply through by 7 and get negative 4/7, 3. So what we really have are two coincident planes, which are acting as one, and a third non-parallel plane intersecting it along a line, and specifically that line is the position vector of 31/7, 0, 3/7 plus the parameter times the direction vector. So we have a consistent system. There are an infinite number of points on all three planes, all lying along that line.